All right, great. Okay, thanks for the introduction. So I understand that I'm standing between you and coffee break, and I'm also literally blocking you from going to the bathroom. So, but please try and ask questions because I'm afraid I don't have enough material since I only prepared 150 slides. So today I just want to tell you a little bit about the work that we have been doing in building data-intensive applications and systems. So from social networking websites to running physical simulations, buying plane tickets online, even running bank transactions, we interact with applications that store data on persistent storage on a daily basis. So how do these applications actually structured? So in a typical case, right? So these applications are usually written in a general purpose language such as Java or Python, and they sit on top of an application server. So, and then there's also a separate database management system that is sitting on top of a database server. So when a request comes in, right? So let's say you go to a web page or you play a game on your phone, what happens is they would interact with the application sitting on the app server, and periodically the app would interact with the database sitting on the database server in order to request and manipulate persistent data. So our group has been focusing on optimizing these kind of applications and also helping developers build new kinds of data-intensive systems. So what is the problem with this picture, right? So this looks very rosy, but in reality, unfortunately, things don't really look that way. So for instance, this piece of application sitting on top of an app server doesn't really look like that. In reality, it actually usually is separated into different components. So for instance, some part of your application might be running a SQL query that is being executed on top of a database system. Some part of this application might be running some sort of distributed data processing programs like Spark that is being executed on top of yet another framework. And yet another part of the application might be doing something like image processing, which is basically getting executed on the GPU. So as Cheung talked about yesterday, we've done this study where we looked at open source web applications, and we found a bunch of performance problems in these kind of applications. So these are not kind of the toy examples that you might find people doing projects or their homework. Some of these are actually quite interesting applications, such as GitLab and things like OpenStreetMap, where some of you might have actually used them before. Just look at the number of performance issues that we have found, right? So what kind of performance issues that we found? Some of them are things like code getting translated inefficiently to different queries. Things about retrieving unnecessary data, data model problems. Some of them Shan already talked about yesterday. The takeaway, right, however, is that many of these performance problems can actually be fixed using very few lines of code, right? And you can actually get a lot of performance benefit out of it afterwards. And these, as I said, right, are not simple toyish examples that people are doing for the homework. These are actually things that have been developed by expert developers over the number of years, right? So our group has been focusing on fixing this problem of how you might get into performance problems if you choose the wrong kind of framework to use, right? So that's one of the things that our group has been working on. So in addition to web applications, we have also been working with scientists. So for instance, LSST is a set of telescopes that are currently being constructed in South America in the mountains of Chile. So these guys are basically going to expect around 12 terabytes of data being captured every single night. And they are basically trying to do analysis, right? Maybe they're trying to look for new planets, so on and so forth. So we talk to them, and then we ask them, what kind of data architecture do you have, right? What kind of software pipeline do you have? They show us this picture. So the details here are not important. What I want to highlight is the fact that there are these kind of individual silo-looking things, right? Which is basically database jargon for one specific database system. So all of these database systems actually were custom built by the LSST team. Each one of them, one after another. So we asked them, okay, so what do you actually do on top of these kind of customized database systems? So they show us one of these pipelines, which again, each of these red boxes are custom operators that these teams actually built. So of course, as good database people, we immediately laugh and make fun of them, right? We basically say, well, you guys are crazy, right? You shouldn't be doing all these things custom built, right? There are all these existing open source tools and even commercially available things like MySQL, Postgres, Oracle, SQL Server, so on and so forth. You should be using those instead of building your own. So they came back to us and basically told us that you try it. right? So we of course took the challenge and we basically look at their pipelines, and we also talk to like neuroscientists, right? So they basically do the same thing. So for instance, here's like one example of the kind of workload that the neuroscientists would have built, right? We took on the challenge, we tried to re-implement all of these pipelines using existing open source tools, right? That was the name of the game. So we're not building anything customized. We're only using open source tools, and like I was actually responsible for one of these implementations myself. And it turns out to be quite a bit of a humbling exercise for us, to be honest. So for instance, we have ended up like, doing things about like, just running out of memory to begin with, right? That's bad, okay? And turns out that each of these operators have multiple implementations to choose from, and it's always hard for us to actually decide on which one to use. And as you can see here, right, the kind of performance benefit that we get, right, by scaling the number of nodes actually changes for different systems, depending on how many nodes that you use. So all these kind of like big data, like, implementation details stuff, like it turns out to be quite a bit of a problem. And then at the end, we basically acknowledge to them, right? We say, okay, great, you guys actually did the right thing. Using these open source tools is not like the immediate solution that we can come up with, okay? So what I'm trying to get at here is basically saying that, like, building these new data pipelines, these new data-intensive systems is just hard. It's just difficult. So for the second part of the talk, I basically want to tell you a little bit about the kind of work that we've been doing to help developers build these engines easily. Okay? So let me first focus on the first thing that I was mentioning with regard to the developer point of view. So they have these kind of different frameworks that they can choose from to implement the application. And as I've told you guys earlier, and also in Shan's talk yesterday, choosing the wrong framework or the wrong API can lead to drastic performance difficulties. So to be concrete, let me go through one very simple example. So let's say we want to implement a row-wise mean in Java for a matrix, where a matrix is represented using a 2D array. You might want to do it in the following way, right? So I first initialize an array that stores the row-wise mean of every single row, and then I basically just iterate through the array in a nested loop fashion. I go through every single row, initialize the sum to be 0, I go through every single column, sum up the values, and then at the end I just divide by the number of columns, right? This is simple enough. So notice that this is basically a nested array programs over arrays. Now, on the other hand, let's say I want to actually utilize Spark to do the same thing. So here's an equivalent program, except that it's written in Spark. So the details here are not important. I basically have a bunch of mappers and reducers and whatnot. The goal that I'm trying to make here, right, is that this is actually a huge semantic gap between these two things. On the left-hand side here, we have a loopy program over an array, versus on the right-hand side here, I have a functional program over resilient data sets, or RDDs, right? So the challenge now becomes, if I actually wrote the program that looks like this, but I actually want to use Spark to do the same thing, I basically need to somehow manually rewrite, right? From the left here to the right. But of course, as good PL researchers, we know something better, right? There's something known as a compiler that should be doing this for us. We shouldn't be doing this manually, after all, right? And of course, we all took, like, undergrad compiler class, right? We all know the merits of syntax-driven compilation. Right? It's kind of like compile 101. So what do? Of course, we then start to devise different rules, right? To say, okay, if you have a pattern that looks like this, right, where these kind of $ things are basically meta variables, we want to basically convert from this kind of program into something that looks equivalent, except that it's, written in Spark. Okay? Simple thing they can do. So in fact, like, a group of researchers did exactly this thing. So back in 2014, right? So this is kind of like the mandatory word count example from this paper that they wrote in Uppsala. And they basically started by applying different rules that they have devised in order to do this transformation, right? So here's the first one that translates from this Java AST form into some sort of lambda expression form, right? And to do this transformation, they only need to apply a few more rules. And then a few more rules, right? And then even a few more rules, okay? Great, so after 22 rules, right, we finally get to this program written now in MapReduce, okay? Now, please don't get me wrong here, right? So, I think these researchers actually are great. They are basically pioneers in showing that this is even possible to do, right? This is awesome work. But what I'm trying to get at is the fact that writing these rules is perhaps a little bit of a brittle business, right? It's hard to get these rules right. And if you, it's also difficult to maintain, right? So for the grad students in the audience, imagine your advisor telling you that, here are a bunch of rules that some prior grad students wrote, and please try to update them to do the next kind of transformation, right? I don't think any of you want to actually take up that task. And the story doesn't stop there, right? So let's say today we want to convert from Java to Spark. Tomorrow we might want to convert into SQL. We have all these kind of new DSL showing up, and then all the different kind of general purpose language and all that's good stuff, right? It's pretty much like an arms race in terms of coming up with a new translation mechanism. So let's take a look at the problem in a slightly different angle. So again, we have the kind of task here that we are trying to do, right? We want to convert from the left-hand side here to the right. Instead of doing this using syntax-driven rules, so let's say, for the sake of argument, that somehow we designed a high-level specification language. You can think of this as kind of an IR, right? In this IR, we basically have very simple constructs. It only has map and reduce. And it also has things that you can put into mappers and reducers, right? Okay? And the restriction in this DSL is that anything that you construct has to be done via the small grammar that we have here. Everything has to be constructed using maps and reduce, nothing else. So I claim that if we have such a language, then doing translation using syntax-driven rules is pretty easy, because all we need to do is just to write one rule for each of these syntactical constructs in this DSL. And since there are very few constructs in this DSL, then doing this translation is very easy, right? Okay? And on the other hand, unfortunately, of course, the program actually wasn't written using this language, right? It's written using this kind of loopy Java program. So the question becomes, right, how can we actually convert from a representation that looks like this into something that looks higher level in terms of using this DSL? So the way that we solve the problem is by using some sort of inference algorithm. Right? We want to basically convert from this low-level representation into this higher-level thing. So how can we actually do that? So for those of you who are in program verification, you might already spot the fact that this kind of DSL actually is something known as a post condition. It is a logical statement that says what needs to be true if the loop actually terminates, right? So in this case, I'm basically claiming that the output here, right, the mean variable consists of a 3-stage map reduce, right, with a bunch of mappers and reducing functions, right? So this is known as a post condition, and in order to assert that this is indeed a valid post condition, since we have a bunch of loops, in program verification, we also need something known as loop invariance. So these, again, are basically logical statements that says what needs to be true while the loop executes. So what does that, and then there's actually a well-known theory that allows us to check whether a given post condition and a loop invariant is actually true. These are known as verification conditions. Some of you might have heard of this before, right? Came from Wicker's preconditions. And in English, right, they basically say something like the following. In order to check that the post condition is true, we need to find an invariant, and the invariant needs to be true when we first enter the loop. The invariant needs to be preserved when we try to execute multiple iterations of the loop. And finally, the invariant needs to logically imply the post condition if the loop actually terminates. So you can see that there's a very mechanical process that we can check, right, to see whether any given post condition and invariant is actually true or not, right? Of course, the question now becomes where do these post conditions and invariants actually come from? I mean, we came up with this language, but the input program was actually not written in this form, right? So that's where program synthesis comes into play. So for those of you who might not be familiar with program synthesis, the idea of a program synthesizer is that it would take in a bunch of different inputs. It would take in a description of the search space. It would take in a bunch of constraints that govern what needs to be a solution. And if you turn the crank, then the program synthesizer hopefully would come up with an expression from the search space that satisfies the constraints. Why am I telling you about synthesis for this problem? Well, because the solution constraints I was referring to earlier is exactly the verification conditions that I was referring to on the previous slide. And on the other hand, what about the search space, right? What are we actually searching over? We are basically trying to search over all the post conditions and invariants, right? But how do we actually write them up? Well, it turns out that we can actually just do very simple, lightweight static analysis to figure that out. So for instance, given the same program that we have seen before, we can do simple data flow analysis to figure out that there are two matrices that we are trying to, two arrays that we are trying to manipulate. And furthermore, there are a bunch of different operators like plus or addition or division in this case, right? And given that, we can now try to guess different loop invariants and different post conditions written using this high-level DSL that we just designed. Okay? But of course, being good pre-L researchers, we basically try to encode this as a grammar, right? Because that basically succinctly describes the entire search space, right? That we can then put in to the program synthesizer. So we now have both pieces of the puzzle. So we have a way to describe what is a valid solution, known as the verification conditions, and we also have a way to express what is the search space that we are looking over, right, encoded using this grammar form. And if we turn the crank, then hopefully the synthesizer will come up with a bunch of post conditions and loop invariants that would allow us to validate the transformation that we are trying to do. So how does the synthesizer actually work internally? I don't have a lot of time to explain that. But for now, I'll just tell you that we basically use an algorithm known as counterexample guided inductive learning. Details are not important here. What I want to focus on is the fact that this is inductive learning. So we're not having another syntax-driven thing, right, buried inside the synthesizer. Because if we do that, I basically just eat up my own words, right? Because I basically tell you that we shouldn't be doing this in a syntax-driven way. So in reality, however, we actually do a lot of different tricks to make sure that this synthesis process actually terminates relatively quickly. So for example, we try to solve incrementally by growing the grammar, right? So we initially try a very small grammar and see if that works out. If that works out, we are already done. If not, we try to increase the size of the grammar by throwing in different operators and see if that works, right? And we also do multiple stage verification, in this case, in using a theorem prover as well to basically check for validity. So there you have it. So we have this original program written in a loopy way, and we designed a high-level specification language that allows us to do syntax-driven compilation from that into something that we would like to do, like to run. And then using this inductive program synthesis process, we're basically able to find these kind of loop invariants and verification conditions that we are looking for in terms of validating the transformation. Yes, question, Mark.
I have a question on so with this, I assume you mean Segis kind of loop. So this would, the verification here would be expensive, and then, so you would expect to have the hypothesis of Segis holding that there is the invariant that you find, if it's correct on the few selected examples, it generalizes to all the data.
That's right.
So that means that you must be finishing in few iterations. The Segis loop must not be running 100 times.
Well, okay, great. So the first question about runtime, we have a bunch of examples later on that can illustrate that. So the second question about unrolling a number of loops or something, if I understand you correctly?
And I mean the Segis loop, how many times you call the verifier, right? You guess a verification condition, then you get a counter example. This must be you must have small number of such iterations, right? Typically,
right.
Yeah.
So hold on to that thought in just a second. I'm going to show you some experiment results actually that illustrates how fast this whole process actually is. Okay. Okay, but going back to this, right? So I actually claim that this is kind of the best of both worlds, right? Because as I just mentioned before, right? Syntax-driven compilation, the complexity of doing this, right, is driven by the number of input constructs that we have in the language. So as I said, in this case, the input language only has very restricted syntactical form, right? So translating from this high-level language into something concrete that you can execute is fairly trivial. On the other hand, program synthesis is entirely driven by the size of the search space, right? The larger the search space, then of course the longer that it takes to actually search. So having this kind of high-level representation also makes it easy to do the search, right? Precisely because of the fact that everything must be computed using a bunch of map and reduce, right? So we're really restricting the search space by quite a bit using this high-level language. So we call this approach verified lifting. This is called lifting because we are basically going against what a traditional compiler would do, right? We're actually converting from a low-level representation into a high-level one just so we can basically port to another target language, right? And this is verified because anything that comes out from the synthesizer, we basically make sure that they are semantically equivalent to the input. So let me illustrate that with one of the compilers that we have built, right, using this technology. And this is exactly the kind of example that I was referring to earlier about translating from Java code into Spark. So the way that this compiler called Kasper works is the following. So we take the input application code, we try to identify different code fragments that might be amenable, right, to this kind of transformation. For each of these code program fragments, we then go through this process, right, of synthesizing loop invariants, post conditions, and then actually generate code, right, for any one of these code fragments where we're able to find a valid post conditions for it. And then after that, we just basically stick it back into the original program. And then now we have this new shiny program written in Spark. Okay? So to evaluate this whole tool chain, we took a bunch of different benchmarks that we have able to collect from open source. So they range from very simple things like classical word count, right? Exactly what the other compiler that I've shown you earlier actually did, all the way up to doing things about image processing, and then even trying to implement page rank and regression using vanilla Java. And at the end of the day, we were able to convert around 80% of all the benchmarks. There are a bunch of cases that we failed. And the reason for the failure, right, for instance, is because of the fact that some of these benchmarks call some external library functions for which we have no idea what is going on. Right? So we can't convert because we can't prove something that we don't know what is going on. Right? There are a bunch of cases where the grammar that describes the search space is not sufficient. We put a timeout to this search process, and then if the grammar by then has not grown to be sufficient to represent the post condition or the loop invariance, then we simply just bail out. And finally, there's also a bunch of cases where synthesis is simply timed out, right? Even though we know that the solution actually lies within the search space that we have already provided as part of the grammar. So what about performance, right? So we're able to translate all these benchmarks, but do they actually perform? So here's a bunch of benchmarks that I've selected out of the 80 or so that we're able to translate. And mode here is the other syntax-driven compiler, right, that I was referring to earlier. So unfortunately, they are not open source, so we can't really compare with them over a bunch of benchmarks that they did not use for their experiments. But for the ones that they have used, right, we have pretty much quite competitive in terms of performance, in terms of the code that we're able to generate. And we're also able to generate a bunch of, translate a bunch of other benchmarks as well. So in general, right, this is kind of getting quite a bit of speed up, but I don't attribute any of this speed up to us, right? We're able to speed up all these applications simply by rewriting them and making use of the Spark optimizer to figure out how to actually execute. So we are only the enabler, right, for these existing programs to use these frameworks. We actually didn't do any of the optimizations ourselves. Yes, I know.
Yeah, so Alvin, how complex are these benchmarks?
Great. So these benchmarks range from about very short word count, I mean you can imagine how many lines that is, all the way to maybe 200, 300 lines of Java code. Right.
And do you have an understanding of how, what's the, I mean, you do this automatic translation, right, synthesis, but what is the, if you do this manually, carefully, right, can you do much better?
So I promise that he actually hasn't seen the slides before, right? Because that's actually what we did afterwards, right? So the question was how do we know what is the limit as to how much performance gain you can get? So we went out and we hired a bunch of Spark experts that we were able to find on Upwork, right? And then here's a bunch of results that we got, right? So you can see that we are pretty much quite competitive against manual implementations as well, except that for this 3D histogram, for instance, right? They were able to beat us by quite a lot. And the answer turns out to be because they realized that Spark has a specialized data structure just to do 3D histogram computation. And we don't know about that in our grammar, so therefore we are not able to find a translation that uses that kind of data structure. So therefore we suck in terms of performance, right? But perhaps the thing that you might ask, right, is how long does it take to do this kind of compilation, right, as Martin was asking. So the mean compilation time is around 6 minutes, median is around 2. You might still say, well, this is really slow, right, because if I do Java C, this should return in seconds, right, so you guys take minutes, right, this suck. But I think that's kind of the wrong measure to actually evaluate this, right, because the really good measure to measure against this is really the human labor time, right, that it takes to actually manually rewrite all these things, right, and for us, namely, for my grad student, really, right? It actually took him weeks, right? To actually go to Upwork, find all these expert programmers, interview them, make sure that they're comfortable, get all these benchmarks afterwards, and then actually run them, right? So I think that is actually the valid measure. Yes, please.
So the Spark code that you generate, that you synthesize, that can be optimized as well. Do you do some optimization there as well? For example, reduced by key is better than other.
Okay, great. So the question is whether we actually do any kind of specialized optimization, right, when we try to look for a translation. The answer is not really, because we basically rely on Spark to do these kind of transformations internally. That said, we do have a cost model to try to limit or to try to reduce the size of the program that we get, because we know simple things like 2-stage map reduce is better than 10-stage map reduce, right? So those things we do know. But then for kind of detailed optimization opportunities, we leave that to Spark because we think that that is something that Spark should be good at doing. Okay. Yeah, Shastra.
Do you know how much time it took experts to actually implement?
Okay, do we know how long it took the experts to implement? So I think out of maybe a month or a month and a half that actually took my students to finish this, we took like 2 weeks to find and interview them, and then we basically gave them 1 month to implement this whole thing afterwards. Okay. So each one of them would give them one single benchmark, right? So this is Upwork, right? It's kind of like, Mechanical Turk. So we gave them 1 month. Some of them never returned to us. Some of them took like, just a couple of days. Some of them took like all the way up to a month to actually come up with some implementation that they think is the most optimized one. So we actually asked them for the best thing that you can do, right? Because if we just get some toyish like translation, that's kind of also defeat the purpose. So we asked them, show me the best thing that you can do, right? Okay, so just to recap, right? So this is kind of like the benchmark, this is kind of like the tool chain that we have using verified lifting. And since releasing this tool, we have gotten a lot of requests by saying that if you can do Java to Spark, can you also do like, Java to SQL, C to Java, all that good stuff, right? So we decided to actually open source this whole framework so that like people can kind of build your own compiler, right? So this is basically what we are currently working on right now. So the goal is for someone, a compiler builder, right, to basically tell us the kind of code fragments that they would like to compile. So for instance, like, loopy programs, and then tell us like, the kind of the DSL description, right, the high level language that they have designed to represent the input programs. And then also tell us like, how to actually generate executable code out of the post conditions that we're able to synthesize. So we have actually used this tool chain to build a bunch of different compilers since then. So the first instance that we used this for was converting Java into SQL. In this case, we model SQL, the relational language, by just a bunch of high-level operators that, for instance, implement selections and joins and whatnot. We took the web application code that we were looking at earlier that basically iterates through persistent data, and then we automatically translate them into SQL, and being able to get a bunch of performance benefit by just utilizing what the database optimizer is able to do. Again, we're only enabling these tools these code, right, to utilize the new frameworks that we have, in this case, database, a relational database, right? I mean, the relational database internally does all the magic optimization itself. We have also took code written in the last century, right? This is basically Fortran stuff that is from the Department of Energy, and they basically have very loopy programs over stencils. These are basically arrays. The language here is very simple. We only need to model different array operations like getting and storing into an array. We took these loopy Fortran programs and then we convert them into Halide, which is a DSL for image processing by running them on CUDA, right, or GPUs. We'll get a bunch of speed up just by utilizing the Halide compiler in this form. So we have also done this for hardware. So we have taken a subset of the C language known as Domino. In this case, they want to compile this to a specialized programmable switch produced by Barefoot Networks, which is now acquired by Intel. And we basically need to model in this high-level language a bunch of specialized gates and architecture elements that is provided by this specialized programmable switch, and we're able to compile a bunch of different data plane algorithms and routing algorithms using this mechanism. So we have also been engaging with different companies using this tool, and now the whole framework is actually being developed cooperatively with different companies as well. And I can also tell you that some of the code that we have actually translated is now getting into production with one of these commercially available image processing tools company that I'm not able to tell you the name, but you can guess from the slide which one it is. Okay, so now let me switch gears to talk about the second part of the talk, but before that, let me see if there's any question that I can actually answer with regard to that. Yes, Peter, please.
So I'm wondering, what assumptions do you make about the initial Java code, right? I mean, you basically gave the impression that computing verification conditions is a solved problem, but if you have dynamically bound calls, heap data structures, pointer aliasing, it's not that simple. You need a very rich logic to express that verification.
Yes, of course. That's a great question. So the question was about how do we model things like pointers and all the nastiness about for instance, memory, right, and all the stuff, right? So we only do this kind of minimalistically. Because, for instance, some of the languages that we have to deal with, like Fortran, doesn't really have these kind of pointer constructs that people use. But for something like C, for instance, right, we do have to model some part of this, and that you are right, that is exactly getting expensive as well. So, but then the nice thing about this is at least for the program fragments that we have been dealing with, they don't tend to have a lot of these aliasing relationships, because if they have a lot of these aliasing relationships, then it doesn't make sense to translate them to GPUs anyway. Right? So that's kind of one of the benefits of this high-level approach. Yes, question, please.
I was curious as to how you actually check the verification conditions. So it looks as though you have to basically compare two MapReduce programs for some kind of entailment or equivalence.
Right. So we actually verified the found host conditions and loop invariance using a theorem prover. So we both use Z3, CVC4, and also Coq to actually try to verify in all of these cases. So anything that comes out of it is guaranteed to be sound, right? Because we are actually able to verify for real. But then, as I said, right, there are definitely cases where we either fail to verify them or we fail to find post conditions and whatnot, right? So it's definitely incomplete.
Okay, thanks.
Okay. Yeah, question.
Do you only need verification? Presumably, a small number of test cases suffice.
Right, great. So the question was do we actually need formal verification, right? So can we just do model checking, for instance? So that's an interesting question because some of these engagements, we actually talked to them and they were saying that they actually don't need us to verify, and we've up front, right? We basically told them that this is an incomplete process. There's definitely cases that we can't verify, but they were actually telling us that they don't need us to verify because they have something called humans to do the verification. They only need us to basically generate the actual code, right? So it all depends on the use case. Some of them basically said that we want push button thing. We cannot deal with this, if they are not actually formally verified. So it all depends on the situation. Yeah.
Is the generated code then readable?
Is the generated code readable? Well, it depends. So some of it is readable by grad student standards. I haven't tried reading all the code myself, so there are definitely cases, for instance, where we compile to hardware. The intention of it is it's actually not supposed to be readable anyway, right? Because it's actually just machine instructions, right? In that case, so yeah, that was actually not part of our goal. But that's a great question, right? In terms of how do you maintain code being generated this way? Yeah.
So do you do anything about floating points, or do you just assume everything is reals?
Okay. Do we do anything about floating points? So the answer is kind of. So for the Fortran compilation stuff, we do have a lot of floating point numbers because that's the input code. So we do have to model some floating point stuff, and then you probably know about how good solvers are, right, in terms of proving those properties. But for other cases, in the Java case, we don't have to actually deal with them because just the fact that the input code don't tend to use floating point numbers in the benchmarks. Okay, so let me move on, right? So now let's talk about what happens to the data system developers. So we talk about the application developers, right? Needing to choose among the different frameworks and APIs that they can use. So now let's talk about what happens to the people who want to actually build a new database engine, right? Like the scientists that we talked to, okay? So let me give you a very brief overview of what happens inside a data processing engine or a database. So what happens is the application would issue a query. So for instance, in this case, SQL, the parser of the database would basically convert this into a kind of AST form, right? So for instance, in this case, we are trying to filter from the employee table and sort by name, so on and so forth. We construct an AST out of it. And then the optimizer will basically try to choose among the different equivalent plans, right, that it can do to execute a query. So for example, our simple filtering can be done using an index lookup or scan through the entire input table. And likewise, we all know about the different flavors of sorting that you can imagine, right? So at the end, right, the goal of the optimizer is basically trying to come up with a final execution plan that hopefully is semantically equivalent to the input, only that it is faster, right? So I claim that there are two things that anyone who wants to build these kind of data engines have to be worried about. The first thing is whether the actually generated plan is performant, right? I mean, we have a bunch of plans that we can generate, so hopefully this is actually the fastest thing that we can do, right? Because after all, that's what database engines pride themselves on. And the second aspect, right, is actually whether they are the two actually equivalent. In terms of if I execute this in a naive way, right, using very simple, without the optimizer, is this actually equivalent to the final plan that the optimizer ended up choosing? You might think, I mean, this is a trivial problem, right? Given that development of relational database has been going on for the last 40 years or something like that, right? This got to be a solved problem. So let me formalize that a little bit, right? So what do I mean by equivalence? Equivalence here is it the case that for two given queries, if I pass in any sort of database in it, they always return the same output? Right? And on the flip side, right? So does there actually exist a particular database where when I fit into both these queries, they will actually return something different, right? Meaning that the two queries are actually inequivalent. So we already saw a talk yesterday, right? Talking about finding bugs, right? And implementations of these databases. So Needless to say, right, if I go off to Google to search for like wrong results, right, there are actually a bunch of different things that people complain about. Right? I'm not surprised by doing that, right? So you might think this, again, would got to be a solved problem. Well, it is kind of a solved problem, except that we already know that this thing in general is undecidable, right? So that's bad. However, people have actually worked on different fragments of, let's say, just a SQL language to show that they are actually fully decidable. So the question becomes, can we actually build a solver, right, that can allow us to reason about relational queries, right? I'm using relational queries as an example because if we can solve relational queries, there are also all kinds of, that opens up a bunch of doors, right? That allow us to basically reason about Spark programs, Hadoop stuff, TensorFlow, and all the kind of cool machine learning languages that are basically appearing on the horizon, right? Okay, so what did we end up doing? So we ended up building a tool that uses two parts. So on the one hand, we try to use an SMT solver to help us find counterexamples for two given queries. On the other hand, we also use a proof assistant to actually try to find validity of the proofs. We built this tool called Cosette that actually try to do like both solve for these kind of relational queries, and I'm going to explain to you why we have two parts and what is in the name. Okay? So let me first go through this kind of SMT solving procedure. And for those of you who might not be in formal methods, the way that a solver works, right, is the following. You give the solver a formula. So in this case, I have two logical formulas here. I know that this is like Saturday morning, so don't worry about it. I can basically tell you that these two things are actually equivalent logically. Okay, so this is just like distributivity of a disjunction. Okay, so you send this formula to a SAS solver. The SAS solver is basically going to consider all these variables here, x, y, and z, to be symbolic, meaning that we don't know the values of them, right? The goal of the solver is to basically try to prove us wrong by, for instance, finding an assignment of these variables such that it will break this assertion that we are claiming, right? So for instance, in this case, like as I said, these two formulas are actually equivalent, so the SAS solver will actually tell us a model, right, or an assignment of these symbolic variables that would basically just prove us wrong. Okay? Why am I telling you this, right? Because after all, we have queries and relations, right? We don't have these kind of Boolean formulas. So this is what am I talking about? Well, it turns out that you can model queries and relations using a similar mechanism. For example, a tuple can just be a list of symbolic variables. A relation is simply a list of tuples. And finally, a query is just operations over relations. What do I mean by that? So let's say I have a relation here called employee with ID and salary as two different attributes. So I'm going to create a relation in this case, right, where both of these are symbolic variables. Again, these are things that we don't know what actually are its value, right? Okay, so I create a symbolic relation this way. Let's say I have two queries, right? So in this case, I'm trying to select the employee IDs of everyone who makes over 100K. And in this case, if we run over on this symbolic relation, all that we will get is a constraint. This is a constraint that basically says that if the first row here, right, the salary, if it is indeed greater than 100K, then we basically know that the output, in this case in red, has to be equal to the input employee ID, right? Again, this is all due to the fact that we don't know what is actually being held in these symbolic variables. So all that we have, right, is basically an assertion. Okay? So that's what happens when we try to execute, right? So-called execute, a query in this case. We can execute another query. So for instance, in this case, I'm trying to select all the employees that makes over 50K. We get something exactly the same, right? Except that the predicate here is different. So now we can send both of these, right, to the SAS solver, right, and then see, right, if it actually is able to find us a counterexample to prove that these two queries are actually not equivalent. So we send it over to the SMT solver, and the solver is basically going to come up with a counterexample. I mean, you and I know in this case that these two queries are actually not equivalent, right? For instance, if the concrete value of this relation is actually such that the salary is 60K, then if we send it to the first query on the left, then it returns nothing, versus if I send it over to the right query, it actually returns the first row. So therefore, these two queries are not equivalent. Okay? You can imagine using SAS solving this way, right? Well, but what happens if I have a relation with one row and then the solver fails to find any counterexample? Okay, well, so we keep increasing the size, right? So you can say, okay, now we actually have a relation with two tuples instead of one. Let's try the whole thing again and see what happens, right? So in this case, we might be able to find a counterexample, we might not, so we keep increasing up until we basically say we give up, right? This is known as incremental solving. A lot of you might already be familiar with that, right? This is great, except that if the two queries are actually equivalent, then we'll be waiting for quite a while before we actually come up with any counterexample, right? That's not good. So what do we do in that case? That's where the second part actually comes in. So that's where we actually use a theorem prover or a proof assistant in this case, right? How does this work? So let's say I actually want to prove to you that these two queries here I'm showing you on the slide are actually equivalent. And you should be able to see that they are actually equivalent, right? Because the only difference between these two queries is the fact that on the left-hand side, I am doing the unioning of the two relations before doing the filtering, versus on the right-hand side here, I'm doing the filtering first before doing the actual combining together, okay? So I hopefully can convince you that these two queries are actually equivalent. How can we actually assert that, right? We all know about like writing proofs, so let's try to write an inductive proof on the size of the relations. In this case, we have both R and S, so we basically just need to come up with an inductive hypothesis, right? I mean, I'm not going to bore you with the details here. So like you basically try to assume that they have n tuples and then the two queries are equal, and then if we have one more tuples, then like the equivalence still holds, right? So on and so forth. So you can do this manually, or I can utilize like grad students to help us do this, right? But this actually doesn't quite scale, right? Because like this is a very human-intensive process. Yes, I know.
Yeah, so Alvin, can you use, for example, the theory of arrays in SMT solvers to also model this?
We can use the theory of arrays, but then the theory of arrays is also undecidable in general. So therefore, we still have the problem of not being able to prove things in general.
That's right. Yeah. Well, the general problem, of course, is undecidable, but
yes.
At least you leave the hard work to the SMT solver.
Great. So let me show you what happens at the end, and then you can ask us questions afterwards. Okay. Okay. So like we all know that like this kind of technique doesn't quite scale, right? Because it requires humans to keep writing these kind of proof scripts, right? But the lesson that we can learn here, right, is that there is actually a way, right? Because if I can write down these kind of inductive proof, right, we can actually send this over to a proof assistant, such as Coq, right, or Isabel, and these proof assistants will actually tell us that yes, these two queries are actually correct. This proof script actually is true. Okay? It's just that we don't have the ability to write these proof scripts manually. So, and also the fact that is we need to come up with all these inductive hypotheses, which even by grad student standards, right, is just impossible. So there got to be a better way to do this, right? So what do we end up doing? So it turns out there's a better way to model relations in a functional way. By that I mean the following. So instead of modeling things as a list, so let's model relation as a function that you give me a tuple and I tell you the number of times that that particular tuple shows up in the relation. It's a number. It's a number, it's a function that takes in a tuple and returns a number, right? 0 in this case just means that it isn't in the relation, right? Okay. And what does a predicate in this case mean, right? Predicate is basically just a Boolean value. It returns either 0 or 1. If a given tuple actually passes the predicate, then it's going to return 1. On the other hand, if not, then it's just going to return 0. So this smart idea actually didn't came from us. It actually came from a bunch of guys back in 2007, right? So this is the way that they model relations. Okay? So you might imagine, like no one in the world is going to implement a database system using this kind of form, right? Because this is a function, right? So how can you actually implement a database system like that? Well, but turns out that this is actually very useful when we try to prove things to be equivalent, as you will see. Why? Because let's say I have this query again, right, from the previous slide. So this is again the union query, right? In this case, what happens if we use this kind of encoding is that it now all of a sudden becomes a bunch of algebraic expressions. So for instance, I try to find out the number of times that a given tuple T actually shows up in the output in this query here. What do? I first find out how many times that tuple shows up in the base relations, R and S, and then since I'm unioning the two relations, that translates into addition over integers. I mean, what a surprise, right? I mean, this is not actually that difficult to see, right? Because if the tuple T shows up 5 times in the first relation and 10 times in the second relation, then if I combine them, it just shows up 15 times, right? Not rocket science. What about the predicate? As I said, right, the predicate is being modeled as either something that returns 1 or 0. So if the given tuple actually satisfies the predicate, then it just gets multiplied by the number 1, right? If not, it gets multiplied by 0, meaning that it doesn't show up in the output relation. Beautiful, okay? So this is how we actually model these queries. And on the other hand, let's say I have the other query that I was trying to show you, right? We can go through the same process, except that in this case, since we're doing the filtering first, we just ended up multiplying by the predicate first before doing the addition. And now, to see that these two queries are equivalent is trivial because we just need to tell the theorem prover that this is just a distribution of multiplication, and that is good enough for the proof assistant to say that, yes, these two queries are actually equivalent. So it basically boils down to algebraic manipulations in this case, right? And as you can imagine, we can generate this proof script kind of automatically by trying out different ideas and see which one actually passes the theorem prover. Yes, there's a question in the back.
Maybe it's different for other examples, but in this case, you could also just give it back to the SMT solver, right?
Sure. So in this case, we can also definitely go back to the SMT solver in this case as well, but it gets into a little bit of a problem after we have summations. Why do we have summations? I'm not going to explain in details here, but summation is actually needed in order to model things like key constraints. And in order to model things like foreign keys and all that kind of good stuff. I'm happy to talk about this offline, right? But once we have summations, then we are talking about in the land of algebraic equalities involving all these different operators, right? So that's not easy. Okay, but in any case, right, so like we basically model all these different relational operators algebraically and then ended up proving things equivalent this way. And that basically completes the picture, right? So we use an SMT solver to try to come up with counterexamples. In this case, we use Rosette that is being developed at Washington. And for the equivalent queries, we basically generate proof scripts that we send over to Coq. So now you understand why we're calling this Cosette, right? Because we are basically taking Coq and marrying it with Rosette. It has nothing to do with the play, right? I've got asked that question many times. Okay, so to evaluate, right, we use a bunch of different benchmarks that we can find, including like real-world optimizer bugs, all the way up to like questions from undergrad database class that we were able to find from instructors, and they both include inequivalent and equivalent queries that we know, right? And at the end of the day, we're able to prove pretty much quite a bit of them to be inequivalent and also equivalent. Most of them, in fact, solve in a relatively short amount of time. So I just want to give you one final example of the kind of examples that we're able to prove. And this one came from 1982. So back in 1982, someone proposed this kind of rewrite that says I can translate a nested query into two different queries using a group by. So I understand that this is Saturday morning. I'm not going to quiz you on your SQL knowledge and say whether these two things are equivalent or not. They claim that they're equivalent, but they basically miss a case about grouping a group that actually has zero values. They ended up making a mistake there. So it's actually not equivalent. Okay, so trust me on that. And if you don't trust me on that, you can actually read up on another paper 5 years afterwards in 1987, where someone basically said you guys were wrong. Okay? But unfortunately, by then, this kind of translation has already been implemented in all the database systems at that time, right? So that is unfortunate. It took 5 years for these guys to realize that there was a problem. We sent this over to Cosette, and it took all of the 10 seconds to actually find a counterexample proving these two queries to be inequivalent. And if I did my math correctly, that's around 15-something million times faster, right? Of course, it's a joke. So you guys might think, well, these guys might be a bunch of jokers, right? I mean, they just propose some random things, and then who knows what happened, right? I only take this as a quote from a book written by Stonebricker and Joe Hatterstein that basically validate, right, that this person, Won Kim, right, for those of you who might not know, is actually a pretty smart guy. So this stuff is just non-trivial. So we have actually released this tool. You can actually try this now. And since we have released this back in July 2018 last year, we have gotten a bunch of different postings. People have translated our user manual into, I believe this is Italian and Chinese, right? And then right now we're actually using this tool to check equivalent rules in the open source Apache project called Calcite, along with Microsoft SQL Server as well. And of course, as an academic, we are definitely using this to grade assignments, right? So that, that's exactly that. All right, so I'm going to finish up this talk here. So I don't have time to talk about the final thing, which is what happens with the performance question, right? So we can now check that the final plan generated by an optimizer is actually equivalent to the input, but what about performance? So it turns out a lot of it has to do with data structures that is being used inside the database server. And I don't have time to talk about this in detail, but we're basically currently working on a new tool called Chestnuts that actually automatically synthesize data structures to optimize query execution plans. And we can talk about that offline if you're interested. So to sum up, in this talk, I basically tell you a little bit about using synthesis to build compilers. I told you about different ways that we can encode relations, and hopefully that can generalize to different kinds of query languages beyond relational ones. And I've also told you just like, in 5 seconds about a new tool that we're doing that uses synthesis to try to come up with new data structures. And of course, I need to thank all the students who I have the fortune to work with. All the great ideas actually came from them, and all the bugs are actually mine. Right? And and of course, I also thanked all the industrial collaborators and also a bunch of different academic collaborations that we have, for example, with Shan's group. And thank you very much. I'm happy to take questions.
So I guess during the talk, we probably have asked a lot of questions, and now also we're eating into the break time. So I guess we can maybe, Alvin, you can take some questions during the break, yeah? Okay, yeah. All right. So let's thank Alvin, and then we'll take a break for 15 minutes. Yeah.